In this video, I want to take a look at vibrations when the forcing function is just a pulse. Right? This is not actually part of this differential equations course, but if we did one more section, it would be. Right? But it ties together some of the things we did here with springs and with Laplace transforms, step functions, and those things. Okay? So here's my differential equation. I got y double prime plus 2y prime plus 2y equals u0 of t minus u1 of t. So this just turns on at 0 and it shuts off at 1. Okay, so just 1. So the forcing function is just a hit, right? It's actually interesting when you think about, problems like shock absorbers, right, on your car. Right? The forcing function on a shock absorber usually isn't a sine wave or something like that. The forcing function is usually you hit a bump. It just happens and then it's done, right? So you were riding on smooth road, then you hit the bump, and then you're riding on smooth road again. And so this type of discontinuous step function is something that you're going to have to deal with. How do those shock absorbers react to that instantaneous bump? So taking a look at this here, the b squared minus 4ac on this thing, b squared is 4, 4ac is 8, so b squared minus 4ac is negative, so certainly this is going to have vibration with exponential decay. So the 2 is fairly high amount of damping. And the initial conditions I'm starting with is that this is a spring system, and the spring is starting at rest, not moving at all, at its equilibrium point. So it's just going to sit there. We're going to hit it with a forcing function for 1 second, or 1 unit of time, whatever that is, and then stop. So I'm going to solve this differential equation by taking the Laplace transform of both sides. And the Laplace transform of the second derivative is 2 times the... actually, I realized that these notes were made a while ago before I knew how to do the fancy script, so I'm just using a capital L for Laplace transform instead of the script L. But anyway, this is the Laplace transform. The second derivative is 2 times the Laplace transform of y minus s times y of 0 minus y prime of 0. Then I've got plus 2 times the Laplace transform of the first derivative, but the first derivative looks like this, s times the Laplace transform of y minus y of 0, and then I've got 2 times the Laplace transform of y, and on the right-hand side of the equation, I have the Laplace transform of this one minus the Laplace transform of that one, and the Laplace transform of those step functions is e to the 0s over s and e to the minus, well, right, because it's u sub c of t would turn into e to the minus c of s divided by s. So this is a minus 1 s over s. Okay. E to the 0 is, of course, 1, so these two get together to look like that. I've also, this is a 0, that is a 0, that is a 0, so everything on the right-hand side that's left has an L of y in it. So the L of y gets factored out, and I got an s squared plus 2s plus 2 right there. So when I divide both sides by that, I get that the Laplace transform of the solution to this differential equation is given by this, which now I just need to take the inverse Laplace transform to find out what it is. And the way I'm going to do that is I'm going to split this up by using the distributive property. So this gets divided into the 1 and into that, like this. And I'm going to need to do some partial fraction decomposition on this first part, which is going to help me on the second part as well, because it's the same denominator. Essentially, it's the same thing with just this multiplied by e to the minus s. So let's do partial fraction decomposition on it. This s squared plus 2s plus 2, I already noticed that b squared minus 4ac was negative, so it's unfactorable. So I'm going to leave it as this. There should not be an s in that denominator. Let's change that. Yeah, that's what it should look like. So we now multiply both sides by this denominator, and the s will cancel out for that one, and that quadratic will cancel out on the other one, and we end up with 1 equal to this. I'm going to plug in some values of s to see if I can find a, b, and c. So plugging a 0 in, I get 1 equals 2a, and that just all goes away. So a is equal to half. Plug in a 1 here, I get 1 equals, I've already plugged the half in for a. So 1 plus 2 plus 2. This is b plus c times 1. So b plus c equals, so this is, what's that, 5? So 5 halves. Subtract it off from the 1, so that's a negative 3 halves. Then I'm going to plug in a minus 1. So plug in a minus 1, I get a 1 on this side. The a is still a half. 1 minus 2 plus 2, and this is minus b plus c times minus 1. And so distribute the minus 1, b minus c is equal to, get all those numbers together there, it's equal to a half. So solving for b and c from these two last two equations, I get that b is minus a half and c is minus 1. So I have that this fraction here is equal to a half over s, and then the b, this was bs plus c, so minus a half s minus 1 on the top there. Okay. Now, I am going to complete the square on this one. So I look at that s squared plus 2s, and I say, hey, that needs to be an s squared plus 2s plus 1. So I'm taking this 2 and I'm splitting it up into a 1 plus 1. So that this then is an s squared plus 1 on the bottom. Then I'm saying, well, I got an s squared plus 1 on the bottom. I want an s plus 1 on the top. So I'm taking that s and I'm turning it into an s plus 1 and then compensating. By throwing a plus 1 in there, it's times a negative a half. So I've actually subtracted a half from the top. I compensate by adding a half. Okay. So I completed the square on the bottom, and I'm essentially completing the linear on the top. And this looks like this now, right? I'm aiming for the sine and the cosine, right? But it's a shifted sine and cosine. So, yeah, I think I'm ready. Oh, I factored a half out of the whole thing. So there we go. And then, what did I do? Ah, yes, I distributed this over that plus sign. So this denominator into that, this denominator into this, to break it up like that. And there is a minus sign out in front of all of that. So there's minus in the minus, right? Because that minus came from those halves. Anyway. Yeah, isn't that great? So we take the inverse Laplace transform of that. The half comes along for the ride. The 1 over s is just a 1. This is looking like a cosine, but shifted. That this is shifted, so the cosine is multiplied by this exponential. And this is an s minus minus 1, so it's an e to the minus t here. And likewise here, this is looking like the sine, the Laplace transform of the sine, but shifted. So again, the e to the minus t is there. Okay. So we had the Laplace transform of y is this, which means now y is, so this part was easy enough, we just did. What happens with this exponential here? Well, that exponential meant that this function, because I see this is 2 videos back, right? Because there's an exponential there, that means that the function was, on the function side, it was shifted because the exponential is on the transform side. Okay, so there's a shift of 1, and all of these things have to be t minus 1s. And apparently, it's just a little too big to fit on the screen. Maybe if I can shrink the font down a little bit, you can see it a little better. I think I can do this. Yeah. So this part is just that, and then there's minus, essentially the same thing, but shifted by 1 times u1. Okay. Looking at a graph of the function here, for the first unit of time is when the forcing function is on. So starting at 0 from rest, this thing is being accelerated. This spring is being accelerated. At that point right there, the forcing function shuts off. So there's a positive velocity that continues on until the spring pulls it back, and then it bounces with very quickly decaying bounce. But this first part is the forcing function, and then the forcing function quits, and then you have unforced damped vibration. Okay. This is fairly standard analysis of spring system with a discontinuous forcing function. Laplace transform and steps functions help us to solve these things. Anyway, it's been a great class. Hope you enjoyed it.